Hello.
Hi,
How are you today?
good.
Let's
I just
see.
had my biz midterm.
Oh, Biz 2C?
Biz 101.
Oh, Biz 101. Yeah. How did that one? You just did it today, or did you got the results back today?
I just did it today.
Oh, how did that go?
Pretty good.
That's good. That's good.
It's more confident
Mhm.
than Chem.
More confident than Cam? Dang. Is it like the Punnett square? Like this stuff?
Yeah, yeah. That
Yeah.
was like midterm one. We're learning
Oh,
the translation transcription now.
oh, translation, transcription. Yeah. I
Yeah.
see. You're more of a bio person than a chem person?
Yeah, definitely.
I see. So, let's see, what can we do today? Let me see. Oh wait, Joseph, do you have any questions on aromaticity, anti-aromaticity, non-aromaticity? Because that's gonna be part of the next midterm too.
I don't think so right now, but maybe if Sin have any, then I could jump in and help out.
Oh, okay, okay. Yeah, so Joseph is he's not in UC Davis, he already graduated. He's a CSU graduate. Yeah, he's just like here to like help or something.
That's cool.
Let's see. Seven, seven, see. Right, let's see. What did he end off last time?
I think he did aromaticity and
Oh, right.
finished the whole chapter, maybe.
Uh-huh. With the frost diagrams.
Yeah.
Let's see. Okay. Right. Let's see. So first, do you have any questions so far? If not, we could go over like his last lecture material or do practice problems on whatever concept you have questions on.
I was just doing random practice problems
Uh-huh.
today,
Yeah.
and I will like, yeah, a lot of them I didn't know what to do.
Oh, I see, I see. So I'll make you co-host so you can share your screen and then I could work on it on the Zoom board and then walk you through it as well. Like last
Okay.
time. Like was it the AETC Maria Jones one?
Yeah.
Let's see.
Uh, Wait, how do I share it? Oh,
Yeah, on Zoom it should have share screen and then you can share your um
oh,
yeah. Oh, okay. I see it. Nice.
Oh, yeah. For the first one, I was confused. Like HBr, I thought, do we get like a Br in each carbon, or like the final product was a double bromide on the first
Ah,
second.
mm-hmm. So this one that you drew right here. Oh, wait, hold on. What the heck? Go back. Let me change the color. Okay. This one that you drew it here would be if your third step was let's say BR2, two equivalents. Okay. But we have HBr, 2 EQ. So let's draw in that product after the second step, which is this one right here, and react that with HBr. It doesn't matter which carbon we grab to form the carbocation because they're both equally substituted. Let's say we grab that hydrogen right there and kick out the bromine right there. That's going to form this carbocation right here. And we know that the Br minus got kicked out, which is going to attack that carbocation right there. And that's going to give us this product after the first EQ, but we have two equivalents of that, so we're going to do that whole thing again, where this time it does matter which carbon attacks the hydrogen because this carbon here will give us the more stable carbocation. So that
Oh,
means
okay.
that this other carbon there attacks the hydrogen, kicks out the Br, and gives us this intermediate where the Br minus is going to go in and attack that carbocation and give us this geminal dihalide here. Right? And you also said bromine is more electronegative than H, so that's why it chooses that carbon. Oh, that's another good thing to talk about as well, where we know that bromine is more electronegative than the hydrogen here, right? Making this carbon here more partial positive and this carbon here less partial positive. And then that is the better nucleophile. That's also another way to think about it as well. Like the carbon on the left is a worse nucleophile because it's attached to a electronegative atom. The carbon on the right is a better nucleophile because it is attached to a hydrogen which is less electronegative than bromine. But another way is to form the more stable carbocation here. Those are two ways to think about it. Mhm.
Okay.
Uh-huh. Right.
So if like we started with a asymmetrical like,
Mm.
oh wait, never mind. Can we end up with a symmetrical alkene?
Yeah, we could end up with an asymmetrical alkyne if your step number two was not CH3I. If it was like, let's say CH3, CH2I, then you would get this asymmetrical alkyne right there. And then if you react
Okay.
that with HBr two equivalents, you would get two different products. Practice drawing the two different products somewhere on the board if there's space. But you don't have to draw the mechanism, just predict the two different products.
Um, eh,
Yeah, nice. Those are the two different
okay.
products. Uh-huh. Let me respond to this person really quick. Okay. Okay. Yeah, that's it. Where if we had BR2 instead, right? This is the mechanism right here. Wait. Wait, who's drawing the red arrows, Joseph?
Oh no, it's me.
Okay, okay. Okay. So let's say we have this internal alkyne right here, and let's say we had BR2 instead. This is gonna be the mechanism. Right? We're going to form that bromonium ion ring and get this intermediate right here after the first equivalence, where we have Br on both sides. But we don't stop there because we have two equivalents of Br2. Right. So we're gonna do that whole reaction again, where we're gonna form that. Oh wait, I skipped all the way to the end. I didn't form the ring. Right. It first forms the bromonium ion ring like this. Right. And then we kicked out a Br minus, which is gonna attack one of the carbons, let's say this carbon here, and break open the ring right there. And then that gets us to what I drew earlier, where the two bromines are on both carbons of the alkyne, and the alkyne becomes a double bond. Right. And then since we have 2EQ, we're gonna do that whole reaction again. Form another bromonium ion ring. Give us that. And then the Br minus is going to come back, attack the ring, and break it open to give us what you had originally.
Oh, okay.
Uh-huh.
Oh, then did I did it right for this one? I mean, I
BR2.
didn't get to the last step, but that's
Uh-huh.
my
Yeah,
thought process.
that's right for the first step.
And I just got stuck on the hydrogen. I didn't know what to do
Uh,
with it.
oh, right. So after the second step, you get to this point here. And then you know how when we have this alkynyl anion, there are 5 different reactions it could do. Um, the first one was an acid-base reaction where any proton source like water, H3O plus, H2SO4, is going to be the acid because this alkynyl anion here can be a nucleophile or a base. If we have water, think of that as an acid, and the alkynyl anion is the base, right?
Okay.
Uh-huh. So what is going to happen between the alkynyl anion and the water if that's the base, the acid, if the water is the acid?
Does it take the hydrogen?
Uh-huh. Yeah. It takes the hydrogen from the water, right? It deprotonates the water, or the alkynyl anion gets protonated, like that. Mhm. And that would become this terminal alkyne here that is protonated. And the water got deprotonated, so that becomes OH minus side product there. Let me erase the other stuff so then we have more space. Let me
Okay.
screenshot this first. Screenshot. Okay. Let me erase this stuff. Okay. Okay. Yeah. Okay. So after the third step, we get this terminal alkyne. Now try uh predicting product with that terminal alkyne and HCl one equivalence only, not two equivalents or excess, only one equivalence.
I'm not sure. No? Okay.
Oh, wait. So let's try drawing the mechanism, right? Let's say HCl is right here. There are two possible nucleophiles for this reaction. It could either be this carbon here or this carbon here. Whenever we do this reaction, we want to form the more stable carbocation. So that's going to be the one that's the more substituted one, which is this one. That means that which carbon is going to attack the hydrogen if we want the more substituted carbon to lose a bond.
Uh, the closer one to the ring.
Yeah, so the closer one to the ring, that's where we want the carbocation. That means the one further away from the ring is going to attack the hydrogen right there.
Okay.
Because we want the one closer to the ring to have the carbocation. That means we want the one closer to the ring to lose a bond. That means the other side, the further one, is going to attack the hydrogen, kick out the Cl, and oh yeah, this is right. Going through this intermediate right here, carbocation, and a Cl minus that got cooked out is going to attack that carbocation and get that answer there.
Wait, if the less substituted, like, well, the less stable side kicked out the hydrogen, how did the positive charge went to the,
Oh, on the more sub side right here,
yeah,
right? So you know how the less substituted side here has four bonds, one, two, three, four. The fourth one from the hydrogen right there.
yeah.
The less substituted side here still has four bonds, one, two, three, four, which is why it's neutral. The more
Okay.
substituted side had four bonds, but now it only has three bonds. One, two, three. It
Okay.
lost the bond with the positive charge.
Okay.
Yeah. So whenever you want a carbocation at a position, you want that position to lose a bond to give that a positive charge. If you want that to lose a bond, that means that the other side has to gain a bond. Like the other side has to attack.
Okay.
Mhm. Screenshot this. Okay. Okay. Is it okay if I clear out all the drawings so that we can move on to the next problem?
Oh, yeah.
Okay. Okay.
Uh,
Okay. That's
it's
part
on
of the
my
PDF.
iPad, so.
I thought it was on the Zoom. I was like, what? This is not working.
But like, is that the only product
Um,
from here?
HCl, 2,2,2-PR2, NaH3, H2O, HCl. Yeah, that should be the only product. Did the key say something else?
Uh, yeah. This was the
Leavens.
key.
So Nasiri says the one that we drew was the major one. Levin says that's mixed because for Levens, she says that you can't stop at one equivalence, but the series says that since there's one equivalence, we stop there. For
Oh,
Mascal, he'll follow the series major thing because in his lecture notes, he says you stop there at one equivalence.
okay.
Levens just ignores the one EQ, like he goes all the way through with excess.
Okay.
Uh-huh.
Yeah.
Mhm. Let me
Um,
see.
I just forgot what to do with the mercury.
Oh yeah. So the mercury stuff, think of that as like oxymercuration demercuration from the alkene chapter. And if
Um,
that's the case, is this a Markovnikov or anti-Markovnikov reaction?
um, anti.
Joseph tricked you. Anti is hydroboration oxidation. No, Joseph. Hydroboration oxidation is gonna be anti-Markovnikov. Right, this is for alkene and alkyne. When you see mercury, right? like mercury catalyzed hydration or oxymercury demurcuration, that is Markovnikov. But in this case, we have this symmetrical internal alkyne. There is no like more substituted um carbon. So that means that the alcohol could be on either side. Right. Let's number this 1, 2, 3, 4, 5, 6. And we're going to add an alcohol on carbons 3 or 4. It doesn't matter because both of them are equally substituted. 2, 3, 4, 5, 6. 1, 2, 3. Let's say we put it on carbon 4. Wait, hold on. Going ahead. Okay, 1, 2, 3, 4, 5, 6. Right, we add the alcohol on the more subside, but in this case, it doesn't matter because both carbons of the alkyne, 3 or 4, are equally substituted. Um, that's why I added alcohol there. And the triple bond becomes a double bond. But what do we do next once we get this structure here?
Automerize.
Yeah, tautomerize into the carbonyl like that. And if you reacted it with the third carbon, put an alcohol there, and tautomerize that, that is going to be the same exact thing. It's just flipped or rotated 2 times. Right? That's the same thing because this is a symmetrical internal alkyne. Right? If you had an asymmetrical internal alkyne, then you get 2 different products, and they're mixed different products. In this case, we only get one product because it's symmetrical. Like if we look at this carbonyl here, this carbonyl is next to an ethyl group and a propyl group. Same as this carbonyl here. That carbonyl is next to an ethyl group and a propyl group because that came from a symmetrical internal alkyne. If it was asymmetrical with different groups, then we get a mixture of 2 different products. Mhm. So when you see H2SO4, H2O, and HgSO4, the big sign here is the HgSO4, the mercury. That is going to be Markovnikov, where you add an alcohol on the more subside. For hydroversion oxidation, you're going to see this reagent here, R2, BH, second step, H2O2, NaOH. And the most important thing for hydroversion oxidation is this boron there. If you see that boron, think of anti-Markovnikov.
Okay. It's like boron. I think like antimacaca only has like a couple, right?
Yeah, anti-Markovnikov, there's only a couple, like the hydroversion oxidation one and the HBr with ROR, ROOR,
Oh,
ROR.
okay.
Uh-huh.
Only 2?
Yeah, only two. Yeah, only 2 that I can think of. There's anti-Markovnikov, the hydroversion oxidation and the ROR one. Well, it doesn't have to be ROR. It could be H2O2 as well, but it's the same thing. Yeah.
So for the next one,
Mhm.
where would on which side would the OH form, like the alcohol?
Right. So for the next one, the OD, because we don't have OH anymore, this time we have DTO, D2O, is going to still be the Markovnikov position. So
Oh, okay.
the more substituted side. It's always the Markovnikov. If you see this most important thing here, the Hg, the mercury. Wait, which is this part right here. Okay. Where instead of OH, we're gonna have OD in the intermediate because we have D2O. And
Oh, okay.
we have to include the D at that alpha position, because when we do tautomerization in acidic conditions, you know how that like alkene grabs the hydrogen from the H2SO4? We don't have H2SO4, we have D2SO4. So we can't leave that D as invisible. We have to draw out that D explicitly.
Okay.
Mhm. Nice, nice.
I'm gonna scroll up a little bit.
Yeah. I'll clear the drawings.
Okay.
Uh-huh. Mm, wait. Hello. Where is the annotation tool? Oh shoot. Oh, it's right here. Clear. Okay.
So like for this one, it's anti-Markovnikov, right? Because the turbidal.
Right. This is anti-Markovnikov because that turbidal there, think of that as an R group. And you know how I said when you see R2BH, but in this case it could be R2BD, that's the anti-Markovnikov one. Right. I think this practice is from the AATC worksheet. Let's go here.
I accessed from the Maria Jones folder.
Yeah, it should be this link right here, and this is worksheet 7. Yeah. Mhm. Yep. Yep. So this is anti-Markovnikov, where um when we do this reaction, right? Uh we are going to add alcohol on the less substituted carbon, which is going to be right there. But you notice we have D right there. The other end is gonna have a D right there. Right? Because in the mechanism, that D of the boron attaches on the more subside. Like that. If it was BH, then we don't have to draw that D. We could just leave that as invisible.
Hmm.
Right? And then once we have this enol, we tautomerize into the carbonyl like that. And we still have to keep that D there. We can't leave that as invisible because it's not a hydrogen.
Okay. What? Wait, so we get to the intermediate with the 2 steps?
Oh, right. So getting to this intermediate right here, um, I skipped steps in the mechanism, but the mechanism is longer because you know how hydrogen oxidation is a long mechanism. The most important thing for this hydrogen oxidation is you think of anti-Markovnikov, right? And that means that we're gonna add alcohol on the less substituted side. We have this carbon and that carbon right there. This carbon here is the less substituted carbon, which is why I added the alcohol right there. The more substituted carbon, this one, is going to add uh whatever that boron is attached to, H or D. It could be T as well, like H, D, or T. In this case, it's D, so I added that D on that more substituted carbon right there. Right.
Okay.
And then the enol just tautomerizes into the carbonyl. Yeah. But that's not the whole mechanism. Like the whole mechanism for hydrogen oxidation is like way longer than this.
Okay.
Yeah.
So
But
it's
uh-huh.
anti-Markovnikov because of the second step, not because it's turbidal.
It's anti-Markovnikov because of this R2BH right here, where R could be tert-butyl, R could be cyclo BD. R could be ethanol. It could be something like this, or propanol. BD two. Like R is any random R group. Tert-butyl is just one of the R groups that this works with. It doesn't have to be tert-butyl. It could be methyl ethyl isopropyl cyclohexanol or cyclohexane. Um, but the most important thing here to know that it's anti-Markovnikov is the B, the boron. That B right there,
Okay.
right? Boron, showing that it's anti-Markovnikov. Oh, and also I think you were asking like the second step makes it anti-Markovnikov. I think it does because of this H2O2 right there. When you see H2O2 or ROR, think of anti-Markovnikov because this is going to create some kind of radical in the mechanism. So when you see H2O2 or ROR, think of anti-Markovnikov, the less substituted side.
Okay.
Uh-huh. Okay.
Yeah, I think that's what I have.
Uh-huh. See. Okay. Okay. That's good. Let's see. Do you guys want to practice the electrocyclic reactions? I think Maria has like another worksheet on that, but I don't have access to that worksheet with the electrocyclic reactions. I just have the access to the one she has on her website, but not on her Google Drive folder.
Do you want me to look it up or we're just doing
Yeah,
practice?
yeah. Uh-huh. Can you
Oh,
look up the electrocyclic like ring opening, ring closing with the conrotatory, disrotatory um stuff for Maria Jones folder?
okay.
Thank you. Thanks, Joseph.
Do you want me to share my screen or
Uh-huh. Um, yeah. Can you share your screen?
okay.
Uh-huh. Thank you.
Okay.
Oh, okay. Is this the only worksheet that she has for the electrocyclic one? I think she has like handwritten ones as well. Or
Okay.
uh-huh.
Let me look it up.
Okay.
I'm not
Uh-huh.
really sure.
Uh-huh.
Bryant,
Yeah.
so I have a quick question that's kind of unrelated to what you were just discussing.
Mm-hmm.
So for allylic systems and reactions, I'm kind of anxious about knowing when it's that reaction happening, versus something else. Like, would it be kind of obvious that it's an allylic system? Like it would just be a double bond. Um, like I feel like there could be mixed synthesis problems or predictive products problems.
Oh, like conjugated dienes, like thermodynamic versus kinetic product or NBS reaction or like
Yeah.
um oh, right. So let's go over that first, and then let's go over the electrocyclic afterwards if we have time. So So allylic position, let's say we have something like this, and let's say we react that with Br2 by itself, no water or no alcohol. It could be a non-nucleophilic solvent like CCl4 or CH2Cl2. In the alkene chapter, we know that bromines are going to attach onto both carbons of the alkene like that, right? We know that this carbon here is the allylic carbon because it is one away from the double bond. If you wanted to only add the bromine there, right? We would use like a low concentration of Br2 and light or heat or ROOR. This is the very first reaction you learned in 118A, which is free radical halogenation. Because remember back in 118A, like let's say we have a regular alkane with no functional group on it, and we put that under Br2 and light. This is the very first reaction you learned. We're gonna halogenate the alkane. We're gonna add the halogen here on, since this is bromine, it prefers the most substituted carbon, which is this carbon right here. Like that, right? Where first it goes through a radical intermediate. And this radical here is the most stable position it could be in this example because it is tertiary. All the other positions are either primary or secondary. Once the radical is at its most stable position, we add a bromine, attach a bromine onto that radical right there. Right. So this is midterm 1 material with the alkene stuff, the Br2 under non-nucleophilic solvent like CCl4, CH2, CO2. It's just going to add bromines on both carbons of the alkene. Think of this as a 118A reaction, the low concentration of Br2 with light or heat, where it doesn't go to here right away. It goes through this radical intermediate here on the allylic position. And we know this radical is stable because it could do resonance with the double bond here, like that, right? Where since this radical is the most stable position it could be at, the bromine is going to attach itself there, giving us this product there. But this is a problem because it's really hard to keep this Br2 concentration very low. So the better reaction to use to get to the allylic bromination reaction is NBS and light. Right? So in this case, this automatically keeps the Br2 concentration low because of its structure and like mechanism, right? It does have to be NBS. You could also see NCS, which adds a chlorine at the allylic position instead of bromine. So it could get trickier for this kind of NBS reaction because let's say we have multiple allylic positions. Like let's say we have something like this, like that. And we react this with NBS and light. Okay. So you notice how we have 3 allylic positions in this molecule. 1, 2, 3. The very first thing you do is locate your most stable allylic position that will give you your most stable radical. Since they are all allylic, we ignore that factor. Then we look at the hyperconjugation factor. Which one is the most substituted? The most substituted we see is this tertiary one here. This is primary. This is secondary. So draw in that radical right there at the most stable allylic position. Ignore all other allylic carbons because that's going to give you your minor product, right? So one of our products is going to be the bromine replacing that radical right there. But we know since that radical is allylic, it could do resonance with that double bond right there. giving us this resonance structure here. Right, where we have to draw single hook arrows because only one electron is moving. Right, so here are our resonance structures, where now when we draw in the products, these are our two different products here. Right, everything else are minor products. Like if you drew your radical here or here and then draw its resonance structure, those are minor structures compared to these two major structures here.
So for allylic, do you think he would add like he did in the other midterm where it was like explain this mechanistically or offer a synthesis or some or propose a
A
mechanism or
mechanism.
something with like the reactant and then the product and then you kind of add everything else in? Would he possibly do something with allylic systems or would it more show up in predict the products, do you think?
This could show up as like explain this mechanistically because you can get multiple different products like how he did in the last midterm, how there were multiple different products, and then he drew that out and it looked kind of weird, and you had to like explain that mechanistically. Yeah, this could most likely be on a mechanism problem, like explain this mechanistically.
Okay, and so to recognize it, kind of, I guess it's just practice, because, but
Yeah.
because with allylic ones, you can react with poor nucleophiles, right, in the on the allylic position, and then you can also do nucleophilic, or no, was it nucleophilic substitute? Yeah, nucleophilic substitution, and then also the organometallic
Yeah.
stuff.
And the organic metallic stuff as well. Right. Like ER, MG, MGBR, and then this could be BR. And then the regular 118A organometallic reactions like that. Right. Where this is different for SN1 because let's say we have this primary haloalkane and we try to react that with water, which is a weak base, weak nucleophile, primary substrate. When you have a weak base, weak nucleophile, think of SN1E1, where the very first step in that mechanism is that the leaving group leaves. When that happens, we are going to form that carbocation right there, which is primary, and very unstable. It does not exist. No reaction. But in this chapter, if we have the leaving group on an allylic primary position, so this is not just primary, this is primary allylic, and we have a weak base, weak nucleophile, which is also SN1E1. When the leaving group leaves, this primary carbocation here is not only primary, it is primary allylic, which is able to do resonance, right? So let's say I have something more difficult. Like let's say we have that, and then we draw its resonance structure. And for Pascal, he's gonna say 40 degrees Celsius is thermodynamic, 0 degrees Celsius is kinetic. Draw in that resonance structure. And let's say this is under 0 degrees Celsius. Okay. So if this is under 0 degrees Celsius, which intermediate will the alcohol react with if we are looking for the kinetic product?
It would be the more substituted carbocation.
Yeah, which is this right structure here. That's right, where the alcohol, oxygen, attacks that carbocation and gives us this product after deprotonation step because that oxygen still has a hydrogen, which is going to get deprotonated somewhere in the mechanism and give us that product right there. This major kinetic product, and we know this is the major one because of the temperature given here. the product that I drew earlier here, this is the thermo extra muscle group right there. Thermodynamic product, which in this case is minor because of the temperature we're given here. If we were in 40 degrees Celsius or higher, this would be the major product because it has the more stable double bond, more stable alkene.
So would he always give us the temperature, or could there be a question where it's just like give the product?
If he doesn't give you temperature, then you get mixed products. You get that and that. But one is thermal, one is kinetic.
Mhm.
Yeah, but he did mention temperature in lecture, so he'll most likely give you temperature.
Okay.
So, and the reason why this is the thermodynamic product is because it requires heat or time to get to the more stable product. And the reason why this is kinetic is because it's the one that gets formed the fastest
Mhm.
because of the stable intermediate here. Right. Okay, let me give you an example of problem with NBS and have you predict both thermal and kinetic product. Like let's say, and this. Okay. Okay. And then we have NBS and light. What would be your very first step here?
Creating the radical.
Right, creating the radical. But first, we have to locate all of our allylic positions for our possibilities.
Yeah.
There's one, and one. Let me make this, wait, actually, let me make this like this. Okay. Based on these allylic positions here, which one do you want to choose for your radical to be on?
Is the top one allylic or is that vanillic?
Oh, shoot. The top one here is way too far away. Wait.
Okay.
Yeah. That's not allylic or vanillic because vanillic is the double bond itself.
Oh, okay.
Wait, vanillic. This should be allylic right here.
Mhm.
That was way too far.
Yeah. So it would be the top one because it's the most substituted.
That's right. So that's gonna be a radical right there. Once we have that, what else do we have to do once we have that allylic radical, the more stable allylic radical?
Resonance.
Resonance, that's right. And then from this resonance structure, we know where our radicals are. So let's just put the bromines on where the radicals are based on those resonance structures. So we have that product coming from this radical and this product here coming from this radical here. Right. In this case, is it symmetrical? Looks like symmetrical. Yeah.
Yeah.
They are symmetrical in this case. So there's no thermal or kinetic product because they're symmetrical in this case.
Oh, so if there's symmetry. Oh, okay. Because
Yeah.
they would be the same thing.
Yeah, they would be the same thing, right?
Okay.
Because the double bond here, they're both tri substituted, and the radical here are both tertiary allylic.
Right. And for NBS, it wouldn't be under heat, would it? Because like would you give both products of thermodynamic and kinetic, or would it tell you to give the thermodynamic or kinetic product?
Right. For NBS, it could happen under light, it could happen or heat or roar. In NBS, I don't usually see them asking you like thermodynamic or kinetic product. The thing that I see them ask that is with HX like HBr or HCl or X2 like Br2 or Cl2. And that's when they ask you about thermo versus kinetic.
Okay.
Right. With NBS, they usually want you to draw both products.
Products,
Don't worry
okay.
about thermo or kinetic for NBS.
Okay.
Mhm. Right. See. Okay. Let me give one example where the thermo and kinetic are different, because I wanted to make one example where the thermo and kinetic were different, but it turned out to be the same. Let me see here. Let's say we have this and that. That's there. Okay. And now let's say this is with NCS and light. Okay, how would you do this problem here?
So identify the most substituted allylic position, which would be the one on the right,
Mm-hmm.
and then make the radical and resonance,
Mm-hmm.
and then react at the two positions formed, and then have your final products. And
Mm-hmm.
then I guess you would label which one's thermo and which one's
Yeah,
kinetic.
right.
So
And
the
then
one on the left is the kinetic one, and then the one on the right is the thermodynamic one.
right, because the kinetic one comes from the more stable intermediate. Thermodynamic comes from the more stable double bond, which is tetra substituted versus tri substituted. And in the radical, this is tertiary allylic. This is secondary allylic. Nice.
Mhm.
Yeah. Okay, that's good. Don't worry about the other allylic positions. Like if you put a radical here or here and you draw its resonance structures and give its products, those are minor products compared to these two here that came from the most stable radical there.
Okay, so for allylic, always look for the most substituted position.
Yep. And those will
Okay.
give you your major products. The other ones, ignore.
Okay.
Nice. Okay. Any other questions? Or we can move on to let's say Maria Jones electrocyclic reactions. Yes, I know some of those are confusing because I had questions on that today, and like people were confused on like the thumb rule, like where to move the thumbs.
Can I ask a question about
Mhm.
the pre-lab quiz? I think it's a quick question.
Yeah, pre-lab quiz.
Okay. Can
Yeah,
I screen share?
yeah, you can screen share. Let me
Okay.
make you co-host. Yeah. Okay.
Okay.
Mm-hmm.
Yeah, for this one, I was really confused. I thought it was 1 and 5 that I would react with.
Oh, okay. So this reaction here, you're gonna
Mhm.
learn most likely tomorrow, like
Oh.
tomorrow's lecture. This is the benzene reactions. You did not learn about this yet.
Okay.
Okay, have you learned about EDGs and EWGs yet?
Yeah, I think so. Or I
Uh-huh.
remember a little bit from the content review.
Content review? I see. Great. So if you look at the carboxylic acid group on the benzene ring, is that
Mhm.
an EDG or an EWG?
EWG.
Yeah, nice. Because
Okay.
that atom directly attached to the benzene ring is a carbon that is partial positive or double
Mm.
bonded to an oxygen, which is in EWG. And are EWGs, let's say, orthopara director or meta directors?
Oh, I don't remember.
Oh, okay. That's okay. That's good. Where okay, if you see EWG, right? When you draw
Mhm.
its resin structures, we're gonna have positive charges on the ortho and para positions relative to that. So which positions are ortho and para to that EWG? Which numbers? Which positions? or ortho and para?
I think ortho is like the closest ones, right? So
Right.
like 1 and 5,
1 and 5, and para?
and then para, is that one 3?
Yeah, 3. That's right.
Okay.
And you notice how there's positive charges there? The best nucleophiles in this case are positions 2 and 4 because there's no charge there. It's neutral. Even though there's no charge there, they are better nucleophiles than the positive charge positions. Positive charge positions are like really bad nucleophiles because you know how nucleophiles they want negative charges to attack things?
Mhm.
Right. The positions 2 and 4, they don't want positive charges at all. Positions 2 and 4, since they're neutral, they are better nucleophiles than positions 1, 5, and 3. So
Okay.
it would be positions 2 and 4 um that would react.
Okay.
Right,
Okay,
so let's
thanks.
try that. Let's try
Mhm.
that.
Okay.
Yeah, see. I want to make sure I get it right
Oh
too.
yeah. Okay. Oh.
Let's see. And hopefully, come on. Come on.
Okay.
Okay. Oh, nice. Let's
Okay.
go.
And then I had another quick question
Mhm.
for B.
Yeah.
I thought we said like in the content review,
Mhm.
like if there's an N, I know it's a negative charge, but like because you know like
Yeah.
the lone pair, like if
Right.
the N is next to the double bond, then it doesn't do resonance.
Yeah, it
So
doesn't
like
do
yeah.
resonance, right? That
So
lone pair does not do resonance. That's right.
so then how come B is considered aromatic?
Ah, it's considered aromatic because it fulfills the 3 conditions. It's cyclic, it is planar, and it is fully conjugated. So once it fulfills the 3 conditions, we have to see how many pairs of electrons are resonating. If it's an odd pair of electrons that's resonating, it's aromatic. If it's an even pair, then it's anti-aromatic. In this case, there are 3 pairs, which are the 3 pairs of the ring itself, like the 3 double bonds there.
Oh,
The
okay.
electrons, the lone pair of electrons on the negative charge is not doing resonance. You're right on that, which is why it's not 4 pairs.
Oh,
Yeah.
okay.
If it was 4, then
Okay.
that would be anti-aromatic.
Okay, so just ignore the negative charge.
Yeah, just ignore the negative charge.
Okay. Okay, thank you.
Yeah,
That's all
no
I had.
problem. Uh-huh. Okay. Let's see. Any other questions? Let's see. Okay, let's end off today's session with an example electrocyclic problem with the thumb rule. Okay, let's say we have something like this. Well, actually, let's do 2, ring closing and ring opening as well. Let's do. Okay, so for this one here, we know this is ring closing where the arrows are going to look like this, right? Where we know there are 3 pairs of electrons, which is an odd pair. So if we have an odd pair of electrons moving under heat, what would that be? A con rotatory or dis rotatory? Wait, let me check the thing because I don't remember.
Is it
Okay,
the
I see. I have to try.
heat?
Uh, let's see. With heat, an odd pair with heat, dis rotatory. That's right. Dis rotatory, that means this is con rotatory. If we see that this group here, right, is going up and this group here is going down, that means they are trans to each other. So my thumb is going to be trans to each other like this. One thumb is going to go left, the other thumb is going to go right. For this rotatory, one thumb is going to rotate, let's say, clockwise, like that. The other thumb is going to have to rotate counterclockwise, like this. So I see that they both end up on the same side, so they have to be cis to each other, right? So they both have to be wedges or dashes in enantiomer, right? If it was conrotatory, we know they're trans. one is going to rotate clockwise, the other would want to also rotate clockwise. They both end up trans to each other. So they have to be trans to each other like this. One is wedge, one is dash. Right. So for ring opening, these are the arrows for ring opening, where there are two pairs of electrons that are moving, which is an even pair. An even pair under light is this rotatory, under heat is conrotatory. Right. So let's draw the template of when we open up the ring, which is like that and like that. In this case, we're gonna have two different products. That's why ring opening is probably harder in my opinion, because we know one group is going up, one group is going down from the wedge and dash. If it's this rotatory, one is gonna rotate clockwise, the other way is gonna rotate counterclockwise, which is the other way, this way, right? So they're both gonna face that way. So let's say I go down like that and like that. But this time, let's say one rotates counterclockwise. That means the other one would have to rotate clockwise, like that, because this rotatory, they're both facing up like that. So let's say this one is going up right here. Which one do you guys think is the major product based on these two products here? There's one major, one minor. And this is based on steric hindrance here.
The one on the right is
Mhm.
major.
Right, the one on the right, because the bulky group here is on the out group. This one is minor because the bulky group is on, like, towards the system, towards the conjugated system. Now, for conrotatory, they're going to rotate on the same side. Let's say this rotates clockwise. This has to rotate clockwise as well. They're both facing towards each other or trans, so they have to be like that, like that. It could also be, let's say, counterclockwise. This would also have to be counterclockwise, where they're facing away from each other now, where an isopropyl group is going to be like that and like that. Where we could clearly see that this is major because that has the less steric hindrance, and this is extremely minor because lost steric hindrance, like that. So ring opening is probably harder because you get two different products, one major, one minor, based on sterics. For ring closing, it's probably easier because you get enantiomers. And that is it. Any other questions for today? Last minute questions?
I had a really quick one.
Uh-huh.
So from the pre-lab that she showed, the one that was aromatic and had the negative charge. So if it's with the benzene, I guess, in that case, it's considered aromatic because you're not counting it in. It's like the same thing with like the hetero atoms donating one lone pair.
Yeah, that's the same thing as that.
Okay. But
Right.
then if it's like the pentane or like cyclopentane with like the double bonds or whatever, and then it's like negative charges on top. Like the same thing, but yeah. In
Right.
that case you count it because there's no double bonds on it.
Yeah, there's no double bond on that carbon where the negative charge is.
Okay.
And if there's no double bond there, then that is resonating. Where this lone pair of electrons is now in a p orbital. That is now adjacent to all of these other p orbitals and can resonate with each other.
Oh, but the other one can't do resonance because they're already resonating with each other.
Right. The p orbitals are already occupied by that double bond right there, making this lone pair on an sp2 orbital.
Okay.
Right.
Okay. That makes sense. Thank you.
Yeah, no problem. Yeah. Okay. So that is good. I'll see you guys tomorrow night or either on the review session this Wednesday and Thursday night. Yeah.
Thank you.
No problem.
Night.
Good night. See ya. Bye.